This is the first lecture on subspace topology, and probably there may be 3 lectures on this topic, and this is of course part of a topology series. And why do I need 3 lectures for subspace topology? Usually within about one lecture for 30-40 minutes the teachers will finish it, because subspace topology is very easy to define, and they prove only 1 or 2 results and that's it. But in my experience, I find students have a difficulty in dealing with subspace topology in very abstract cases. And also there are 2 important facts which are rarely mentioned in any course, but interestingly these 2 facts are used on daily basis in either you deal with topology or analysis. So I plan to do that, but that will take second or third lecture, not now. Okay, so stay tuned. And again, do not worry about trying to remember any of those things, just enjoy it. Try to think along with me and enjoy. You will see you yourself can reconstruct a lot of things on your own. Okay, don't worry about exam, whether it will be useful for exam, whether it has been done by the teacher, so if it's not done it may not be necessary. Don't do any such thing. Just follow the course, try to think along with me, develop a taste for mathematical thinking. Okay, so let us go to the tablet and get started. Yeah, this is the title, Subspace Topology, delivered on 16th December. You have my email ID. If you want to suggest something, you can write to me on this. This is the YouTube channel. Okay, this is a shorter channel. This C makes it shorter. C for channel, hopefully. Okay, and then who's the channel name. And the references are these 2 articles. One is essentially outlined about 60-70 pages notes. The other one is specific examples for subspace topology. You may download both of them from this site, which I had given in all my lectures, so most of you may know of that. And remember, you can also do searching in this site, so that if the title which I had given is not exactly the title there, you can still do search, you will get it. Okay, try. Okay, let us get started. So let us start with the X. Okay, add an on paying. So let us start with X tau, a topological space. All right, and suppose A is a subset of X. To avoid triviality, let's assume A is non-empty, right? Okay, then the subspace topology tau A is defined to be the collection UA, U intersection A, where U is in tau. Okay, if you want I can write tau X, but I'm writing tau A, right? So pictorial, this is how it looks like. This is my X and this may be my A, okay, and this may be my U. This is my U, therefore U intersection A is this. Okay, right. So one would like to check whether tau A is a topology. Of course on A, right? That's very easy, because why? Take empty set, take U equal to empty set, therefore U intersection A will be empty set that belong to tau A. And take U equal to X, that is in tau X, tau, therefore X intersection A will be A, because A is a subset that belong to tau A, right? And next, suppose I have collection Vi in tau A, yeah, in I, right? So when Vi is in tau A, what does it mean? That means there exists, yeah, Ui in tau, so that Vi is Ui intersection A. Notice that this Ui may not be unique. For example, here this may be like this, the same thing Okay, this may be also another u dash, so or u1. So u1 intersection a will be same as u intersection a. You understand that? So this u may not be unique. If I say v belong to this, that means there exists some u in tau, so that v is of the form u intersection a. This u need not be unique. Right? Okay. I hope all of you understand that. Very good. Okay. So let's come back. So suppose there exists a collection vi in tau a. I have to say union vi belong to tau a. This is what I have to prove. But I know there is at least one ui in tau, so that vi is ui intersection a. Right? Therefore, what is that I have to do? Let us look at union vi, I in I. This is same as union ui intersection a, I is in I. But notice that this is same as union ui, I in I, and this intersection a. Okay, I hope you know how to prove it. Okay, but since ui are in tau, this is in tau. Therefore, this is some u intersection a. It's of the form where u is union ui, I in I, and this is in tau. Right? And why is this true? That's very easy. Suppose I say a belong to this, that means a belong to some. I'm just trying to prove, because most often, as I keep saying, many students' problem is this set theory. You intuitively believe everything is all right. This is what you want to prove. Suppose I have an a here. This means what? There is a j such that a belong to uj intersection a. Therefore, this implies a belong to union ui, because uj is here, and a also belong to a. This means a belong to union ui intersection with a. Therefore, a belong to this side. Yeah. And conversely, if a belong to union ui intersection a, right? Remember, this means a is in a, of course, and a is in union ui. This means a belong to a, and there is a j in I, so that a belong to uj. That means a belong to a intersection uj. That is your vj. Right? Therefore, x belong, if a belong to this, a belong to this. Okay, this is a very fast thing, but those of you who have never seen such things, please go through this. Okay, and intersection is similar. Suppose v1 v2 are in tau a, then that means there exists u1 u2 in tau, so that vi is ui intersection a. Therefore, v1 intersection v2 is u1 intersection a intersection u2 intersection a, that is u1 intersection u2 intersection a, but u1 and u2 are in tau. Therefore, this is some u which is in tau. Therefore, this is the form u intersection a. Therefore, it also belongs to tau a. Yeah. So what you have proved is tau a is a topology on a. Okay, this is called the subspace topology on a, induced by the topology tau on x. Okay, so let us quickly look at some examples, then we will do that. Okay, so we want to look at lot of examples. So example 1. So let us quickly recall, if A is a subset of X, then tau A, how do I define? It is U intersection A, where U is in tau X or tau, right? Therefore, when you give us B a subset of A, when does B belong to tau A? If and only if there exists U in tau X, so that V is of the form U intersection A. And is this unique? No, not necessarily unique. Okay, I'll give example quickly now. Okay, this is a summary of what you have done. So let us look at some example. 1. Let us start with the favorite thing, my X equal to R with usual topology, usual metric topology or absolute value metric, right? Okay, now let's look at my A to be the set of integers. So I have this, and these are my integers, etc. Right? Now I want to know what is the subspace topology on Z. What is tau A? Question is, describe concretely. Okay, right, that's very easy. Remember, if you had attended my earlier lectures, the first few lectures on topology, I insisted always on something. What is that? Even before I defined the basis, I insisted look for some typical, simple, okay, or basic open sets of a given point. Take a point in the space set and look for, instead of open sets, what you should look for is what are the typical, simple or basic open set containing the given point. So let us start with a natural number n, not natural number, an integer z. What are the typical open sets? Now if z, okay, if B belong to tau A and such that n belong to this, then B is of which form? B is of the form U intersection A, that is U intersection Z, where U is open in R with the usual topology, right? Now n has to be there, right? Therefore n belong to this, therefore n must be in U also. And what are the simplest open sets which contain n? So this is my n. Simplest open sets are the form n minus epsilon to n plus epsilon, right? Now in particular, I can avoid this n minus 1 and n plus 1 by choosing epsilon less than 1. For example, epsilon equal to half. If I take, then therefore I take u equal to n minus half to n plus half. Then u intersection z is nothing other than singleton n. Do you understand this? So what do you think I have proved? Okay, I have proved, okay, singleton n is open in A, that is in Z. That is singleton n is in tau Z. Do you follow that? Because n is an open set intersect with Z. You got it, right? Therefore, in other words, this n is arbitrary. Therefore, what I have done is every singleton n is open in the subspace topology. Therefore, what is the topology? Therefore, the subspace topology is on Z is discrete, right? So pause, review, proceed. Okay, now notice that this singleton n is n minus any epsilon intersected to Z as long as 0 less than epsilon less than 1, right? Therefore, if you call this as u epsilon, okay, now what I am trying to show, you understand? If you call this as v, this is u epsilon intersection, this u epsilon keeps varying. The same set u b can be obtained as u intersection A with different A's, different u. That's what I am proving. Have you understood? So that u, so when I write V equal to u intersection A, this need not be unique. Keep all these things, okay? Right. Now let's look at another example. Okay, suppose I take A equal to, let's say, 0, 1. So this is my 0, this is my 1. Right? Now let's look at what are that in tau A. Suppose V belong to tau A and 0 belong to V. Okay, I want a description of V. Again, what am I looking at? I am trying to find this example 2. I am trying to look at the simplest or typical or basic open set containing the given point in the subspace topology. So this V must be of the form u intersection 0, 1, right? And remember 0 belong to this, therefore 0 belong to u, and u is an open set. Therefore, what are the simplest open sets which contain 0 in the usual topology? They are of the form minus epsilon to plus epsilon. Do you understand? Therefore it's of the form minus epsilon to plus epsilon. I am just taking epsilon to be less than 1. It may be greater also, but just for fun I am taking. Okay, therefore what is this then? If I take u equal to minus epsilon to plus epsilon, then u intersection 0, 1 is 0 to epsilon. This here it's open. Okay, therefore what is the conclusion? The simplest open sets in tau A containing 0 are of the form 0 to epsilon open, 0 closed, epsilon 1. Now epsilon is greater than 1, you will see it is all of the full interval 0 to 1, the full space A. Do you understand? Now let's look at this set. Let us say, okay, this is my 0, this is my 1, and this is my sum AB. 0 less than A, less than B, less than 1. Now let's look at this set B, which is the open interval AB. Okay, question is, does it belong to tau A? Is it open in the subspace topology? But that's obvious. How many of you think it's obvious? Because this actually belongs to tau, the usual topology. Therefore this intersection 0, 1 is itself, because AB is contained in this. Therefore AB, because of this is contained in AB in the interval 0, 1, therefore it's AB. Okay, therefore it belongs to tau A. Right? Now the question, what are the typical sets containing 1 which are open in the subspace topology? Again the same question, right? So how do I do that? So this is 0, this is 1. Now if V contains, V is in tau A and 1 belongs to V, then this is of the form u intersection A, and u is in the usual open, the tau usual topology. Therefore u is an open set containing 1. What are the simplest typical open set or basic open set? They are of the form 1 minus epsilon to 1 plus epsilon. Right? So it intersection, therefore V is of the form 1 minus epsilon to 1 closed. Do you understand this? Therefore this is open in the subspace topology on 0, 1. So in particular, let me look at this. 0 by 1 by 3 open, union 2 by 3, okay, okay, yeah, 2 by 3 to 3 by 4 open, union 9 by 10 to 1 closed. This is a subset of 0 1. Is this open in the relative topology, subspace topology? Yes, because we know this is open in the subspace topology, this is open in the subspace topology, this is open, right? Therefore, what do you get? The union of open sets. We know that tau A is a topology and each one of them belong to tau A. Just now we proved it. Yeah, therefore there is a finite union, therefore that's also tau A. Okay, so pause, review, proceed. Go through this example carefully, learn that well. Okay, now let's look at example 3. Suppose again my x equal to r with usual topology and my A equal to the set 1 by n as n varies over n, union 0, singleton 0. Yeah, now what is the subspace topology? Right, now if you have, you should develop intuition. This is 0, this is 1 half, 1/3, 1/4, 1 by n, etc. Okay, 1 by n. Now I'm sure your intuition should be good enough. Okay, if I take x equal to a, x in a, there are two cases I have to deal with separately. How many of you know what are the two cases? If x belong to a, then I want to consider case 1 and case 2. If you look at the picture, intuition should help you. The case is when x equal to 1 by n for some n. That is, x is not equal to 0 or x equal to 0. These are the two cases, right? Now suppose x equal to 1 by n, right? And suppose b belong to tau a, therefore v is u intersection a and 1 by n belong to this. So I'm just magnifying. This is my 0, this is 1 by n, okay, and 1 is far away, okay, because I have magnified it, right? Now what are the typical open sets containing 1 by n? Of course you will say 1 by n minus epsilon, 1 by n plus epsilon, right? But if you think little more deep, you will see, look at this 1 by n plus 1 and this by 1 by n minus 1. This is an open set U in tau u. Do you understand this? This is 1 by n plus 1. This is 1 by n minus 1. Therefore 1 by n is squeezed in between, right? Therefore this u, which is 1 by n plus 1 by 1 by n minus 1, this is an open set in tau u. Therefore u intersection my a is singleton 1 by n, right? Therefore what do you conclude? The simplest open set containing 1 by n in the subspace topology on a is singleton 1 by n, right? So if my a, let us look at b equal to only 1 by n as n varies over n, then what is the subspace topology on b? Because now that argument shows each 1 by n is, the singleton is open in the subspace topology. Therefore this is nothing other than discrete topology. Do you understand that? But in a it's not discrete topology. Why? Let us look at 0. Suppose 0 belong to v. This is open in tau a, right? Therefore again look at the picture. this is 0, okay, this is 1 by n, this is 1, etc. And I have to go here, right? Now B is of the form U intersection A, where U is in open set in R containing 0. What are the typical open set? They are of the form minus epsilon to plus epsilon, right? So if I intersect that, therefore if I intersect minus epsilon to plus epsilon, right? So whenever n, okay, that is 1 by n less than epsilon, that means n is greater than 1 by epsilon, right? So implies 1 by n lies in minus epsilon to plus epsilon. Are you following what I'm saying? Therefore my V, which is minus epsilon to epsilon intersection A, is singleton 0 will be there, union all 1 by n, so that n is greater than 1 by epsilon. Are you following? Therefore the simplest open sets, in A which contain 0 are of the form 0 union 1 by n, where n is greater than or equal to some n. Yeah, do you understand? Therefore the topology of A is not discrete topology. But B equal to 1 by n varies over n, tau B is the discrete topology. Learn this example well. In the third lecture I will come back to this. Okay, pause, review, proceed. Okay, now let's look at the fourth example. See, in R itself there are a lot of interesting things we have to do. Yeah, now again take R with the usual topology, but now my subset is Q, set of rationals, right? Okay, now what I want to do is I just want to point out something very interesting. What I want to prove is the following. Suppose let us look at the set V, which is set of all rational numbers, so that minus square root 2 is less than or equal to or less than or equal to square root 2. This is V1. And let's look at V2 to be set of all R and Q minus square root 2 strictly less than or strictly less than square root 2. Okay, so now this is of the form minus square root 2 to plus square root 2 intersected with Q, and this is open in the usual topology. Therefore this is open in tau Q in the subspace topology on Q. Yeah, do you understand? This is by definition. But I claim V1 equal to V2. Notice that this is the closed interval intersection with Q, but I claim V1 is V2. That is very easy, because the only point which is missing, okay, because why is it 2? Because plus or minus square root 2 are not in V1. Okay, you understand? Are you following? Notice that V2 is a subset of V1. This is clear. So I only have to prove V1 is a subset of V2, right? Okay, now what are the, if it's a rational number, okay, think carefully. Suppose R belong to V1, then what does it satisfy? Minus square root 2 less than or equal to or less than or equal to square root 2. Can R be this or this? Plus or minus square root 2? It cannot happen, because R is rational, right? Therefore actually this implies minus root 2 less than or less than plus root 2. But then this implies R is in V1. Sorry, V2. Right? Therefore I have shown V1 is contained in V2. Therefore v1 equal to v2. So what is the moral of the story? Moral is v may be in tau a, but v may be equal to u intersection a, u open in x, and f intersection a, f may be okay, f may not be open. In fact, in this case it's okay, it may happen, but still it will. Yeah, just the thing about. So this shows actually, since f is in this case, okay, that is where a equal to q and my f equal to minus square root 2 plus square root 2 intersection q. Okay, then my v1, which is f intersection q, is open and closed in tau q in the subspace topology. Because what is the complement of v1? This is, you can see, this is intersection of minus infinity to square root 2 union square root 2 to infinity. This set intersect with the q. Okay, therefore this is also open in tau q. Therefore v1 is in tau q, and v1 complement is also in tau q. Therefore v1 is both open and closed in the subspace topology. Yeah, please pause, review, proceed. So tomorrow it's just about okay, 30 minutes only. So let me just take one more example. This is which example? Fourth example. Now let me do a simplest example. 5. Suppose xd is a metric space. And a is a subset of x. Okay, then let tau d be the metric topology on x. Okay, let me just call it tau x. Okay, now so tau x is a topology on x, which is the metric topology. Now a is a subset of x. Therefore I can ask, what is the subspace topology on a induced by tau x. Yeah, now let's start with any a in a. What is that I should ask for? Suppose b belong to tau a, then v is of the form u intersection a, where u is in tau x, right? Now a belong to this, therefore a belong to u. Again the same argument, you see that. Therefore u is an open set in the metric topology and a belong to u. Therefore what are the simplest open sets which contain a in the metric space? They are of the form bar. Therefore I can take u equal to bar. Okay, simplest or typical or basic open sets is of this form, right? Therefore my v is bar intersection with a. Again let us look at the picture so that you should know. So this is my x. Okay, I didn't want it to be a circle, but it happened. Okay, all right. Okay, now suppose this is my a, right? Now suppose I take my a here. Now bar will be this. This is bar in the space x. Therefore this is the set we are thinking about. Open, all are open. Okay, right. This BR is open, but this may be anything, a may be okay, whatever. Have you understood? Keep the picture. Now there is something interesting happens. Now notice that D is a metric on X. Therefore I have the induced metric metric dA on A, right? Therefore dA on A1 A2 is nothing other than d in A1 A2. Think of them as points of X and then take the distance, right? Therefore I have a metric topology on A. Okay, let me call it tau d. Okay, this is a metric, if you want, tau d metric topology on A induced by the metric dA, right? So on A now I have two topologies. One is tau A, other one is tau dA, right? Now what we found out is a typical, okay, open set in tau A is of the form BAR intersection with A. But okay, now let's look at BAAR. This is set of all P in A so that distance between P and A is less than R, right? This is the open ball in A with respect to the metric dA. Do you understand this? But what is B XOR? This is set of all X in X such that distance between X and A is less than R. Now what is the relation between BAR and BXOR? This is BX AR. Intersection A is nothing other than BAR. Why? Because suppose X belongs to this set, that means distance between X and R is less than R, X and A is less than R, and X belongs to A. But remember that is same as X belongs to A, distance between X and A is less than R. This implies X belongs to BAA, right? So what I have shown is the basic open sets and tau A and tau dA are the same, or BXAR intersection A, which is equal to BAAR. They are the same, therefore the topologies are the So many of you may find it little overwhelming. Go slow, repeat again. Okay, keep the picture in mind. This is the only thing you need to understand this example. That's it. Okay. So try go through it. So in the last example, what happened? A is also a metric space. Restrict the metric on X to a metric to get a metric on A. Then I have a metric topology on A by the induced metric. Then look at the topology, metric topology on X that induces subspace topology on A. Right? Now what is the relation between these two topologies? Usually these things are not done. Just go and check. Okay, they are same. Why? Very simple observation. What is the observation? In the induced metric, the open balls I get in B suffix A AR. Okay, the open balls BAR in the space A and is equal to nothing other than the open ball BAR in the space X intersected with A. Right? That's it. So we get the same topology. I hope you like it. Please go through it. Don't miss it because this is usually not done. Observe. Okay, we'll meet again. And now we will look at our standard list of examples like co-countable, VIP topology and lower limit topology, order topology, etc. And try to have a better understanding of subspace topology in the abstract cases here, because all these cases are I can draw picture. There also we will do, certainly we will do that. Okay, stay tuned, we'll meet again.